Okay, so today I'm going to talk about ink recirculation architectures. So what I mean by ink recirculation is basically the continuous flow around the whole of the ink path. And I basically just want to focus on what benefits that gives to the end users. And I'll talk about some additional benefits from some new results. Okay, so first of all, just go through a summary of what I'm going to talk about. So I'll introduce what recirculation in printheads is, the component parts, and what the core benefits that it offers users. I'll then go through all the different recirculation architectures that have been introduced in a variety of different inkjet printheads. And then I'll also obviously a bit of focus on Xaar's implementation, TF technology, through flow technology, and go through some of the benefits of that. But really what I want to talk about is some additional benefits from through flow technology, which are reliant on the actual implementation of the architecture. So some of the new benefits which are reliant on the actual architecture itself. And then I'll finish up with some conclusions. Okay, so ink recirculation for inkjet printhead. So basically, it's nearly 10 years ago since really ink recirculation was introduced for inkjet printheads. And really, it basically transformed industrial inkjet printing. So what it enabled to do is to get industrial inkjet printing really into the factory, proper industrial applications, and we've all heard of ceramic printing and things. And this is really, about 10 years ago, that really made it a reality. And it became obviously adopted across many fields. So really, what are the core advantages? Well, with ink recirculation, it really removes debris and bubbles from the actuator for basically greater jetting reliability. And it really enabled single pass printing. So the ability to give you low maintenance, single pass printing, so in an industrial environment. So simple, you had your printhead, what you wanted to print on passed under the printhead, and it was just a single pass application. So that's what really it enabled. It also, and it refers back to some of the previous two speakers, because the fluid is constantly in motion, you don't have any dead spots in the printhead. It enables printing of heavily loaded, solid loaded pigments without the issues of sedimentation and causing the printhead to block. And of course, the last core really advantage is the improved thermal control, because basically the fluid acts as a coolant for the printhead and for the actuator, so it stabilizes its temperatures, and basically, again, it basically improves its reliability and hence print uniformity. They're the core benefits of recirculation. I'm not going to talk about that a lot. People from Xaar and people from other inkjet printer companies over the last 10 years have talked about that a lot. What I really want to talk about is recirculation has been introduced into many industrial inkjet printheads, and what I want to talk about is how that implementation affects further additional benefits from using ink recirculation as a process. So, recirculation architectures. So, I'll just introduce the sort of components of recirculation and what we actually mean by recirculation. So what we mean is an externally driven flow of ink through the printhead. So you have the ink system, you create the flow through the printhead. And what I've got here is just all the components of the printhead. And so I can reference it for when we compare different architecture. So you have the inlet into the printhead. The fluid is then typically divided in a submanifold. It passes into the actuation chamber. It then importantly passes by the back of the nozzle and then goes back into the submanifold and out into the inlet, and then you complete the recirculation path. So what I want to try and do is use that as a reference for when we compare different architectures. Just a bit of a disclaimer here. I'm not going to go through every architecture that is available. I'm just going to go through some of the main industrial inkjet printhead suppliers and just compare it. And obviously, as they say in the BBC in the UK, there are other ink recirculation architectures available, but I'll just go through some of the main players. And what I'm going to do, and this is quite obviously we'll start off complicated, is just use it by referencing publicly available information, so pattern drawings. So that is from Fuji Dymatics, filed in 2009, granted in 2013, and that is basically their drawing showing and it looks quite complicated, but we can put on some of the common features. There's the ink inlet, where the ink comes in. It then goes to a submanifold, where the ink is divided and then gets access to the chamber. Then they have the chamber, where actuation occurs, and then it goes back to past the nozzle, out through the submanifold, and then it'll complete the circuit. So, as you can see, quite a complicated ink path. And this is typical for a roof mode type actuated device. And if you compare it to another supplier, Xaar, so this is published in 2015, and you can see it's got a pretty similar flow path. Inlet, submanifold, into the chamber, actuation occurs here, it flows down, past the nozzle, out through the submanifold. So again, fairly similar. And again, for Ricoh's, the same. So this was filed and published in 2015. Again, these are pattern drawings. What I am absolutely not saying is this. I'm not the expert in how this is being implemented, but these are obviously indicative drawings. So you have an inlet. It flows to the chamber, nozzle, submanifold, and again, out again. So what are the common features in these typically roof mode type where the actuation is via the roof mode? So typically you can see they've got twisty flow paths through submanifolds, ascenders, and all these type of components. But quite importantly, they have small ink inlets and outlets. And you may say, well, what is the reason for that? And that basically limits the pressure leakage from the actuation. So you can see on the roof mode, you have a single source of actuation. And basically what you don't want to do is all the energy you want all the energy to go out with the nozzle. You don't want the energy to go out with the inlet and outlet. And I don't want to pick on this particularly, but you can see here, actuation down here, you want all the energy to go that way. What you don't want is all the energy to escape to the side ports. So typically, they're always quite small inlets and outlets. But what that does is it restricts the flow path, and obviously restricts the rate at which you can recirculate the ink. So that's one of the things which we'll develop further. If you look at another, and this is not strictly speaking the same because it's not forced recirculation, but if you look at a conic and Minolta head, you can see now, well, at least you have a more open structure, and you also have actuation. Actually, the nozzle is in the center of the actuator, and you can generate pulses from both sides of the actuator, both upstream and downstream. This is probably better demonstrated in a patent from SII, which filed in 2007 and granted just this year. And this is, I'll just explain, this is a cross-section through the actuator, and you have the channels. This is the channel wall, and you can immediately see that it's a more open structure. So you're getting flow, you're getting you got a flow inlet and then the outlet, but also again the nozzle is in the center, and you can get what we call a double-ended actuation. So you can get actuation from both downstream and upstream focused on the nozzle. So you can get pressure pulses going both to the nozzle, so it's not lost to the outside. So you can see with this printer quite a long channel. So it's but it is quite an open structure. If we get on to Xaar, we'll keep Xaar to last, I think. But, so this was filed in 2013 to grant it. And this, I've done it in two diagrams here. So this shows the ink inlet, and this actually feeds two sets of actuators, quite short actuators, and that's the actuator outlet. And this is the a dual recirculation path. But this is probably a better diagram, and this is from one of the original patents in 2001. And you can see it's a very open structure, and the length, you have the nozzles again in the center of the channel, and you have a very short channel, so not to restrict the flow. So you can see here where the ink comes in through the central inlet into the submanifold. The submanifold is directly in contact with where the channels are, so there's no restriction there. Goes across the chamber, which is the channel structure that you see, and you can see the nozzles, and then it returns to the submanifold. So really quite a simple recirculating architecture. So what does this give us? So it's a very open structure and directly supplying channels. The pressure is, as I said, is upstream and downstream. It's what you call a double-ended device, so it's actuation from two acoustic waves from both sides. And it's an open submanifold, and the flow is only restricted by the channels themselves. So, and this obviously was first implemented in 2007 with the Xaar 1001, that's a more detailed picture of the architecture, and obviously that was what started off the revolution in business in industries like ceramic printing with this recirculating architecture. This is kept developing the technology, so this is Xaar 1001. This is Xaar 1003, the latest, doing my marketing bit, latest product this year. But this basically, we kept developing that technology, and this basically, now the Xaar 1003 can print what factories want, can print up to 8 hours, so a full shift without any intervention whatsoever. So no maintenance whatsoever. And these, we've shown, can print over a day's worth without any intervention. So I think the big question of that is, what do we get for this? What do we get? What is the impact of, we've got a technology with high recirculation and an open structure. What benefits does that give us? So we briefly, I know Paddy talked about this briefly this morning, about nozzle latency. So one of the theories was the increased recirculation rate enhances nozzle replenishment in the channel, and then that minimizing the impact of startup on printing. So that was one of the things that you get more exchange in the nozzle, and can it impact nozzle latency and startup? Improved meniscus operating pressure window. So does it improve the pressure window that you can operate the printhead? So you basically, high recirculation rate minimizes the impact of each jetting event. So does that mean that you can operate over a wider operating range? And lastly, does it enable the increased number of grey levels, increasing print productivity? So basically, the open structure means that you can get ink easier into the channel. Does that mean you have less problems with ink starvation, and you can repeatedly pump the channels and achieve higher productivity? So I'm going to address all of these issues today. So first of all, nozzle latency. So the properties of ink, and we talked about it a bit, change whilst idle. So if they change whilst idle through evaporation and curing, that it can impact startup printing. So the hypothesis was, well, does ink recirculation, does that help you to exchange the fluid in the nozzle and then hopefully help nozzle latency and give you better startup printing? So what we did is a series of experiments just to demonstrate that impact. So first experiment, we just looked at the effect of recirculation rate. So with different recirculation rates, we measured drop placement, and just to see if higher recirculation rate, the impact of the idle period was less. So simple experiment, leave the printhead idle for 5 minutes with a given recirculation rate, eject a burst of 10 drops, and then we measured the print quality by just looking at the drop placement, and see if with higher recirculation rates you get better startup print quality. So it's a fairly simple graph. So we all referenced the drop placement to the last drop. So you can see this is after a purge. So you can see it's after a purge, so all the drops nicely aligned. If you had a low recirculation rate, the first drop is missing, and the second one is placed, but the fourth one is pretty much as you would expect. You increase the recirculation rate, first of all you get better placement at the second drop, and then the first drop appears, and then eventually, at the highest recirculation rate, you get the best placement. So basically we've shown that the fourth drop is always stable, and basically increasing recirculation rate so it mitigates the effect of nozzle latency. So the second experiment on the series is with a higher flow rate, what is the impact of the idling time? So basically we left the inkjet recirculating we picked a high flow rate this time, and then we just left it for recirculating for a certain amount of time and then measured the print quality. Same graph, again 5 minutes, you can see the first drop is slightly misplaced. It does get slightly worse with time up to 24 hours, but you can still see that even with recirculation, you can still get all the drops are present, is just slightly misplaced. So, that is, again, mitigating the nozzle latency effect. So, and the last one is really looking recovery time. So this is looking at when you have zero print and zero flow. So you actually switch the recirculation off. And can recirculation help you get back to a better condition? So a lower number of failed nozzles quicker. So this experiment, so leave the printhead idling, no recirculation flow, set the test flow rate for 10 seconds, and then print a burst of 10 drops with a gap, and see and count out how many are affected from that idling period. So results fairly similar. We compared two conditions, one with no flow, so you don't restart it with flow, and then the second one is with the high flow rate that we've discussed, about 125 millimeters a second. So this is with all these experiments are with solvent-based ink, so it's susceptible to evaporation. So we specifically picked the solvent-based inks. So with this, with no flow, you can see even after 30 seconds of idling, the image is affected. And once you get to 5 minutes, all 37 bursts are affected. That compares to 120, where you've got a high flow rate. We can actually see that the first is affected, but even when you idle up to 10 minutes, all of them, the only burst that is affected is the first one. So again, you can see a clear impact through the high recirculation rate. So second experiment is about operating window. So basically what we mean here is the pressure operating window when you can get good printing. So we measured a range of meniscus pressure and we had different recirculation rates. So the experiment set the recirculation rate by setting a differential pressure across the head, and then vary the meniscus pressure window. And at a certain meniscus pressure, we were just comparing whether you get good jetting. I know that's really difficult to see, but take my word for it, that's good jetting. And then we're just looking at bad jetting and seeing at what meniscus pressure window these occur. So the results, this is with a UV-based ink, and you can see, so on this you have recirculation rate designated by dP across the top, and then meniscus pressure, and you can see the window is quite wide, but you can similarly see that it increases as you increase the recirculation rate. And we may think, well, that's a big operating window, but this is one of the reasons why Xaar printheads can be used in skyscraper mode, because we have very wide operating windows with the recirculation technology. So last thing, so this comes back to the Greyscale performance and output. So with TF technologies, just to keep saying this, open recirculating architecture ensures that the ink can get easy access to the channels. So we can see the open submanifold here. What that absolutely means is, and obviously we've got this double-ended, so we're pulsing ink into the nozzle from both sides of the actuator. What that actually means is, with that architecture and with the open structure, it means that we can continue to pump the when we're in grayscale mode, continue to produce subdrops. This is not just into Xaar technology. This is also in, we saw some other technologies before which had a similar open architecture. And what this means is that, sorry, I'll just go back, is that you can print up to seven drops, seven grayscale drops. So you can get the combination of having a very small drop, but also because you can pump lots of them, you can have a very high laydown drop also. So it's quite a flexible product. And what that then means is, and this is operating at very fast frequencies, so you're generating the subdrops at 126 kilohertz for a 1001 printhead. So it's actually operating very fast. So this, we talked about single cycle and 3 cycle and some of the limitations in productivity. This overcomes some of them limitations. And basically that enables us to give 2001 JS12, I know it's a number, but you can compare it with other products, of 360 microliters per second per inch. So quite a really high productivity printhead. So, conclusion. So I think that's pretty much. So what I've shown is, recirculation architectures have been introduced into different industrial inkjet printheads in subtly different ways, and shown that with the Xaar TF technology offering high recirculation rates, and that's one of the key things, that there are additional benefits over all the architectures. It can improve nozzle latency in startup. It can increase meniscus pressure operating windows, and it enables high productivity printing with a wide range of grayscale levels. Okay, and that's it. So thanks to some of the co-authors and then Hanifa who did all the work, and some of these results were previously doing a printing for fabrication earlier this year. So thank you.
Thank you very much, Angus, for the presentation. There are some questions. So, is a high recirculation flow increase the foaming problems?
I'm not an ink person, but yeah, I don't think it's going to make it better. Yeah. But it's something
Definitely
you have to handle.
I suppose.
It's something you have to handle.
Yeah.
Something that's
okay.
what.
But you have to be careful.
Yeah, it's something we have to be. Okay. And obviously, some people have introduced degassers and things like that.
Yeah, of course. Yeah. Okay. And talking about idling time and consequent restart, which is the effect of a really long idling time, maybe some days? Are there some special procedures, or what's the consequence of that?
To be honest, we've actually found that that there's no great procedures. We have to obviously leave it recirculating for slightly longer, but it's absolutely quite incredible how robust these systems are and how easy sometimes it is to restart with increasing recirculation. So,
okay, thank you. About the flow rate, how much is a maximum admitted, or to still keep a printing process stable? Well, does that affect the printing process when you go to extreme values of the flow rate?
I don't think we never we haven't found limitations in that way. Generally, it's how much you can pump around the printhead. It can result in some other unreliabilities, but there again we have to handle them. But it's not issue. It's the problem we have is people don't recirculate fast enough, and it's easy to recirculate very slow. But actually, we want them to recirculate very fast.
Okay.